energy has demonstrated in wartime use that brought to sharp focus the new problems concerning human survival and the urgent need for a civil defense program based on facts about the atomic bomb. Opportunities to gain this information came with the study of structures in controlled atomic tests conducted at Eniwetok Atoll in the Central Pacific. The main objective of testing is weapons development to strengthen national security, but also included are scientific experiments for the Atomic Energy Commission, military projects for the Air Force, Army, and Navy, and defense tests for the Federal Civil Defense Administration, primarily concerned with the effects of nuclear weapons and brick and mortar, with precision and skill, as though it were to last 1,000 years. But it's a weird, fantastic city, a creation right out of science fiction. A city like no other on the face of the earth. Homes, neat and clean and completely furnished, that will never be occupied. Bridges, massive girders of steel spanning the empty desert. Railway tracks that lead to nowhere, for this is the end of the line. But every element in these tests is carefully planned as to its design and location in the area. A variety of materials and building techniques are often represented in a single structure. Every brick, beam, and board will have its story to tell. When pieced together, these will give some of the answers and some of the information we need to survive in the nuclear age. At varying distances from ground zero, the point of detonation, numerous experimental elements are assembled. Underground structures and facilities of various types play their part in duplicating the complexity of the modern city. The vast research program includes testing such items as covering materials, paints, varnishes, plastics, also various fabrics and samples of clothing. On the outskirts of our test city, a synthetic forest has been erected to determine the protective value of foliage and trees. To give us a ringside view of the event, high-speed cameras stand like lonely sentinels, ready to photograph the hurricane of fury. Before leaving the test area, a final check is made on the multitude of instruments and technical devices which will record a variety of blast phenomena for future study. Now, with all the elements in place, our test city is complete. From the air, its center will appear as a bullseye to the bombardier at H hour. On the morning of shot day, official observers, technicians, and scientists gather at News Knob to await the momentous event. This is the payoff for months of planning and preparation on the part of the Atomic Energy Commission, the military services, civil defense, and other test agencies. As part of an experiment to observe the phenomenon of atomic detonation at close hand, military personnel and defense officials dig in within a few miles of ground zero. After a final briefing from the officer in charge just before H hour, the men disappear into their foxholes. Every precaution has been taken for their safety. They're told to crouch low, shield their eyes, and remain down until the signal to rise is given. Now the moment of greatest anxiety, waiting those last few seconds. Seconds later, the blast wave reaches the trenches. As the tower of smoke and flame looms overhead, one thought is uppermost in all minds. Now it's over. The fury of it had stunned some, but not one was injured. High above, the smoke ring puffed by atomic breath rises skyward, watched by the men who had faced it. A scouting party takes the first look at the scattered wreckage of the test city. The imprint left by the hurricane of fire and blast remains here for us to read and analyze. From studies of ruins and damage such as this, we get the hard-to-come-by knowledge that helps us form rules for survival in modern warfare. While only atomic bombs are tested in Nevada, the results can be scaled for the larger, far more powerful thermonuclear weapons. A hydrogen bomb will destroy a greater area than the atomic bomb and will release more dangerous radioactive materials. But the problems of rescue caused by blast and fire along the periphery of damage remain the same. In these fringe areas, civil defense training can save many lives, lessen damage from secondary fires, and help establish emergency facilities. Now in a helicopter, the radiological safety men measure the amount of radiation. When readings indicate safety for human beings, the troops are led in for a tour of the area. By double-checking with Geiger counters every inch of the route, men can now enter safely and confidently areas spotted with radiological contamination, an indication of the progress made in understanding atomic hazards. And thus, each test adds to our growing fund of knowledge. For it is only by investigating and experimenting that we get the facts to keep our military and civil defense program up to date and effective. Every bit of twisted steel makes its contribution. Blackened ruins and ashes of a structure add another chapter. The shattered wreckage of a dwelling offers an eloquent testimonial. Piece by piece, like the parts of a jigsaw puzzle, our story is assembled, analyzed, and evaluated. Another Nevada activity of the AEC was its civil effects program of tests originated by various non-military federal agencies. For example, 2 typical frame houses were exposed to the first blast of the series for the Federal Civil Defense Administration. Some 50 civilian automobiles were included in this test. Several types of family and community bomb shelters were also tried out. The blast from the 16-kiloton shot hits the house at 3,500 feet, around 3/4 of a mile, almost total destruction. The other house at 1.5 miles showed only moderately heavy damage. These visually spectacular tests were only one portion of a big program which included extensive dosimeter and radiation research and important biomedical and genetic studies by some of the country's top scientists. On the thermal effects program, one project concerned parked aircraft and aircraft components, an extension of previous tests. New data were obtained on structural weakening from thermal inputs too low to cause visible damage. Cloth thermal shields were proved to have considerable value in reducing damage to parked aircraft. Some aircraft fabrics were destroyed at levels as low as 2 calories per square centimeter, while magnesium sheet and foil-covered panels were undamaged by 20 calories. It was also found that strong tie-downs may protect aircraft parked nose-on to the blast from much of the damage that will occur if the plane is unmoored and free to lift and roll. But for side-on or tail-on orientations, the tie-downs may actually increase damage. Another important section of the thermal program was a study dealing with normal city vulnerability to fire started by atomic weapons. 3 cubicle houses 7,700 feet from zero were erected for one phase of this study concerned with exterior kindling fuels. The first house has a clean, safe yard, but dry rot is working in the unpainted siding. No rot here, but toys, weeds, and trash against the fence. A clean yard, painted fence, and maintained siding. Number 9 goes off. 13 calories per square centimeter. Overpressure 3.5 pounds per square inch. Time sequence photography shows the results. Destruction on the right from the yard trash which set fire to the fence. On the left, rotted wood in the siding was the ignition point. Sound painted wood and a clean yard allow the center house to survive. The fire hazards in these projects are not unusual either. 6 big American cities were a test of Army prefab Bailey bridges. Shot 9, 4,100 feet from zero. Essentially undamaged, the bridge slid back on its piers as expected, moving 43 inches from a peak pressure of 8 pounds. 9 pounds from shot 10 hits another bridge. Movement out of all proportion to that caused by almost the same static pressure on the first shot. Army equipment, which included 54 trucks and jeeps, was exposed to shot 9 pressures ranging up to 21 pounds to the inch. Thermal input reached 130 calories per square centimeter. Damage was generally moderate, as expected. All but 2 vehicles, one with burned tires and one with a missile-punctured radiator, could be driven away under their own power. For shot 10, Army tanks, artillery, and 22 trucks were exposed to pressures expected to range from 3 to 55 psi. Once more, damage was much greater than expected. Equipment was not merely overturned, but often torn to pieces or hurled great distances, at overpressures from which no such effects were predicted. Pressures which had done negligible damage to identical items on shot 9. Obviously, shot 10 was handing out surprise data. It was evident that our old static pressure criteria were not valid for predicting damage to wind-sensitive targets in the precursor region of low bursts. Not only were there violent high-frequency pressure fluctuations in this region, but the precursor depressed static pressures no longer had the same relation to dynamic or blast wind pressure. 6 marine LVTs, landing vehicles tracked, at distances from 800 to 4,500 feet from zero, with pressures reaching 22 psi, 2,400 feet, overpressure 11 pounds. Damage was light on all vehicles. On shot 10, the same vehicles varied from 1,000 to 3,450 feet from zero, pressures running up to 47 pounds. Shot 10 damage was again unexpectedly heavy as compared with shot 9, with 1 vehicle destroyed and 3 severely damaged in the precursor region, which on this shot extends out to around a half-mile from ground zero. These tests suggest that normal shock waves from high bursts will damage LVTs only moderately up to 22 psi, while low bursts will do severe damage above 12.5 pounds. Curtain wall panels on a series of concrete test cells, some with window openings, some without. The panels were constructed of various masonry materials such as brick, cinder block, clay tile, and combinations of these materials. Similar variety went into roofs and interior partitions. On shot 9, 4.5 pounds overpressure does this: 6,700 feet from zero. 7 pounds here, 4,400 feet range. Unreinforced brick stood up fairly well, though cinder block and transite shattered. Walls with 20% window opening showed much greater blast resistance than blank walls, though damage to interior partitions was high. 3 framed structures with windows and skylights containing various types of glass and plastic glazings were set up at 7,600, 12,500, and 20,000 feet from shot 9. Pressures were 4 psi or lower. A few conclusions that can be drawn now are that quarter-inch clear plastic shattered least of the material tested. Quarter-inch wire mesh was the largest mesh effective in reducing interior missile hazard. Exterior jalousies were worthless, and explosion hardware has very limited usefulness and may even be disadvantageous. Signal Corps placed radial and transverse pole lines, underground wires, and aluminum towers at different distances to test damage effects and determine time required to restore communication facilities. On shot 9, pressures of 7 to 9 psi knocked down the transverse pole lines at 3,500 and 4,500 feet, and partially destroyed lines at 5,500 feet in the 5-pound region. However, radial pole lines end-on to the blast were almost undamaged. Similarly, towers at 3,400 and 4,400 feet were knocked down, and the one at 5,400 feet heavily damaged. At 6,400 feet, the top section of this 240-foot tower was made unsafe by 4.5 psi, approximately 6,400 feet from shot 9's zero. Instrumentation was thorough. A few major types, being pressure gauges at 3 heights, time recording anemometers, pitot-type dynamic pressure detectors, and snubber wire arrangements to measure deflections. Pendulums were substituted for the lollipops of former operations to provide mechanical simulation of tree response. As on many of these projects, camera stations were set up to provide high-speed motion picture coverage of blast effects. Thermal input, 18 calories per square centimeter, resulting in only mild char on tree trunks, since the normal ground litter that will ignite at around 3 calories was lacking. Static pressures around 4 psi. Post-blast survey indicated that approximately 20% of the trees were broken, and the missile hazard from falling trunks and limbs would be substantial. There was scant reduction of static pressure inside the stand, but a 20 to 40% reduction of dynamic or drag pressures. Thermal shielding proved excellent, with negligible penetration beyond the 4th row of trees. 16 items of Army rolling stock were exposed on shot 10 only. A 45-ton diesel locomotive, 1 riveted and 1 welded steel tank car, 13 boxcars loaded and unloaded of various types, 6,600 feet, 2 pounds overpressure, 4,400 feet, 4 psi, 1 empty boxcar turned over, 1 loaded car damaged, 3,400 feet, 6 psi, boxcars damaged or overturned, 2,800 feet, 7.5 pounds, 1,850 feet, 9 pounds, 1,500 feet, before being hit by 13 pounds to the inch. And here's the same view afterward. The frame of one of those tank cars was thrown against a building 200 feet away. A tank car body went 1,200 feet. The whys and hows of these excessive damage effects at static pressure levels where no such results were anticipated will require further study, as will the mechanics of precursor